Number one, determine the asymptotes, holes, and domain of the graph for here of k of x. Now, obviously, we can go straight to the calculator, and for some, that's going to be the easiest way. For others, I'm going to go over the algebra part first, because the algebra, if you know it, you'll never get it wrong. So the first, if we wanted to do asymptotes, the horizontal asymptote, if you remember, is determined off of the rules, either Bobo-Botten or Eats-DC. And I should say horizontal asymptote, there's only one. This one, when I say Bobo-Botten Eats-DC, I'm talking about the powers. You see how these powers are the same? If the exponents are the same, divide coefficients. This falls under the rule Eats-DC. Exponents are the same, divide coefficients. So here my coefficients is 1 or are 1 over 1. And so this means that it's y equals 1 because 1 divided by 1 is 1. That'll be my horizontal asymptote. So if I want to go ahead and put that on my graph here, I know that it's going to approach this horizontally because it's 1 divided by 1 when the powers are the same. Next, if I want to do a vertical asymptote, the vertical asymptote is where it's like the parts where the domain breaks. It's the things you're not allowed to do in mathematics. And so in this case, there's actually going to be two of these because I can see this squared. There's going to be two places where x cannot equal 0 down in the denominator. That's how you solve this. You'd set that equal to 0. And so to solve it, I'm going to factor that. Factors of negative 27 that add up to negative 6 would not be 1 in 27. 2 cannot go into 27. 3 goes in 9 times. It's going to be 3 and 9. 3 times 9 gives me 27. Now to get negative 6, I need this to be 3 minus 9. And if I check, that does multiply to be negative 27. So now I take this power, and remember I split it. I do not change the coefficient, but I split the power, so it becomes just x to the first plus 3. X minus 9 here. All this cannot equal 0. So my vertical asymptotes, or this would be for the domain rather, you would say that x cannot equal 3. And the domain, I'm sorry, negative 3. What I'm doing is I'm setting these equal each to 0 like that, or not equal to. And so here, x cannot equal 9. That would be domain. And so for the asymptotes, they would occur at negative 3 and 9. So I'll add those to the graphs. So for the sake of asymptotes, I'm going to change this to x equals negative 3 and x equals positive 9. For the domain, that's where I would say does not equal 0, like that. So now I'll go and add these to the graph. So x equals negative 3, 1, 2, 3. This is where the x-axis is, so it can't equal there, nor can it equal positive 9, which is off the graph this way. It'll be way over here. You'd have another one. Because that's 1, 2, 3, 4, 5, 6, 7, 8. It'd probably be even further right than this. So we'll have a graph kind of like this. And if I'm circling these as I go, so you can keep track of all my answers. This is the horizontal asymptote here. These are both vertical asymptotes there. It says to find holes. Now holes would be anywhere things cancel. So I need to check this. I might not have two asymptotes here. I didn't even think about that. We need to go to holes next. And so holes exist anytime you can cancel a factor. So if I factor the top here, I would have factors of negative 63 that add up to negative 2. Let's see, 1 and 63 would not work. 2 does not go into that. 3. What about 9 and 7? I'm skipping ahead here. 9 and 7 do multiply to be 63. To get it to be negative 2, then 9 needs to be negative, and that does multiply to be negative 63. So again, I'll split this power. So it becomes x plus 9, x minus 9 times x plus 7. That would be the numerator. And remember how we had this for the denominator? X plus 3 and x minus 9. So you see how the minus 9s cancel out here? That means x equals 9 is actually a whole. So I need to put that answer with it over here for a whole. And this one would not be a vertical asymptote there. That's a whole. So I'm going to change this answer to be like that. And so this line would not be there. I got ahead of myself. And that's why we will check all this in the calculator. So we're going to have a hole out there. And if you want to know what the value would be for the y value, you just plug it in here. So I'd have like, if I plugged it in, the y value, y would equal maybe 9 plus 7 over 9 plus 3, which is 16 over 12, or that's 1.25. So that would be the point where there is a hole. It would be a 9, 1.25. That's where the hole would exist. If you wanted to put it perfectly on the graph, that's where it would be located. Okay, so asymptotes, holes, domain. All right, so the domain I already kind of said is what the values that x cannot equal. So you could write out your domain this way. You could say that x cannot equal -3 and -3 and +9. That's in set builder. Or you could say from -infinity, going left to right, you'd have the first break at -3. From -3, you would go all the way to 9, and you'd have another break, and then you would go from 9 to infinity, like that. This would be my domain. You could write it either of these ways. Sometimes after writing what x cannot equal, they'll do comma, x element of the reals, but that's good enough for me. All right, so let's look at the graph. So we should have an asymptote at -3 and a y asymptote there. Let's go to graphs. It was a fraction, so it's x squared minus 2x minus 63. That was the numerator. And the denominator was x squared minus 6x minus 27. Oh, and I typed in a cube there. I'm sorry. Let me change that equation. X squared, not x cubed. That changed my graph, did it not? So let's go x squared. Okay, so first things to point out. Let's check, does it have the asymptote at y equals 1? I can just add the new equation, and what I can do is type in 1 there, and does that divide the two pieces? It does. We say we also have a horizontal asymptote at x equals, so you go to text, menu actions text, if you want to do x equals -3. We want to see if this breaks. I'll drag it down the x-axis, and we'll see, yes, those are my two asymptotes. We want to check over here at 9, do we have a hole? Because I don't see a break there. Okay, so since I don't see a break, what I can do is I can go to table, Control T, and I can check that at 9, there is a hole there because it's undefined. Remember, anything that's in the domain that does not exist will have undefined, and that's why our domain was x cannot equal -3 and +9 because they're undefined. But the way I know this one's a hole or removable discontinuity is because I cannot see it on the picture. So that is in fact true, and so we did a good job here of graphing these. If I wanted just to fill this in to actually have a graph, I would go like this, and over here you'd have that hole somewhere, and when you draw it on your own, you do something like that on the graph. But that's how this graph would look.